Today on AI Paper Slop, we are covering a paper called Scaling Mixture of Experts Video Pre-Training for Embodied Intelligence. And we are just jumping straight into this deep dive today because the implications here are massive.
Oh, absolutely. This paper introduces LingBot-Video.
Right, LingBot-Video, which is the very first large-scale, completely open source mixture of experts video foundation model. And it is designed from the ground up for embodied intelligence.
Yeah.
So we are summarizing 3 core breakthroughs today. We've got a single-stream sparse MOE architecture that just completely decouples capacity from compute, a robot-augmented data engine, and a physics-aware reinforcement learning reward system.
And to really frame why this matters to you, like if you're building AI right now, you just have to look at the reigning champions of video generation.
Yeah.
Models like Sora, right, or Stable Video Diffusion.
Right, the heavy hitters.
Exactly. They're undeniably incredible models. But, I mean, their underlying architecture prioritizes visual fidelity. They want to make a cinematic shot look good.
Hollywood-style stuff.
Exactly. They do not care about rigid body dynamics or, contact stability or even just physical consistency over long time horizons.
Yeah.
So LingBot-Video is really trying to bridge that gap between passive digital art and active physical actuation.
So the goal is to build an implicit physical world model.
Yes.
Like, we want a model that intuitively understands gravity, friction, object permanence, literally just by watching video. But obviously, before we can jump into scaling up a massive mixture of experts model to learn all those physical laws, the architecture needs a foundation.
Right, a foundation that won't instantly bottleneck your GPU cluster.
Exactly. And LingBot-Video makes a very deliberate, I'd even say somewhat contrarian choice right out of the gate here. They use a single-stream diffusion transformer.
Yeah, they're definitely stepping away from the current meta with that one.
No time.
Because if you look at the landscape today, dual-stream architectures like MMDIT are just dominating everything. Dual-stream processes, text, and video modalities via completely separate pathways.
With those dedicated cross-attention layers.
Right. But LingBot-Video, they use a unified input formulation. So they apply some lightweight modality-specific projections, and then all the visual patches and condition tokens just share the exact same transformer blocks.
Okay, I have to push back on this single-stream choice for a second, though. Because if you are an ML engineer right now, dual-stream is popular for a very good reason. It is exceptionally good at aligning text and video features that have completely different topological structures.
It is.
To me, using a dual-stream architecture is kind of like having a dedicated translator sit between a poet and an engineer. Yes, it adds overhead, but it ensures the nuance isn't lost.
That's a good way to put it.
So by forcing all the data into the exact same language from the very start, doesn't LingBot-Video risk losing that critical cross-modal precision?
It's a completely valid concern. And, if they just concatenated the tokens blindly, the model would absolutely fail.
Right.
That is exactly why they implement a multimodal 3D ROPE. So rotary position embedding. They use this to maintain that structural distinction inside the single stream.
Yep.
They essentially place the text condition tokens and the visual tokens into entirely non-overlapping coordinate ranges.
So how does that actually look in practice, like functionally?
So the condition tokens, they get temporal-only coordinates, which look like I, 0, 0.
Yeah.
Meanwhile, your visual patch tokens get a full 3D coordinate mapping. So that's L plus 1 plus FHW.
Okay.
Yeah, and the query and keyhead dimensions are mathematically split across the temporal, vertical, and horizontal axis. And then the rotary frequencies are just applied independently to each axis.
I see. So 3D rope E maps them distinctly in space and time. But, I mean, does that completely negate the risk of losing structural nuance compared to having dedicated cross-attention layers? Or is this just, a necessary trade-off for compute efficiency?
Oh, it is absolutely a calculated trade-off. It comes down entirely to MFU model FLOP's utilization.
Right, the golden metric.
Exactly. Because if you have ever tried to scale a dual-stream architecture across a sequence-parallel distributed layout, memory bandwidth becomes an absolute nightmare.
Oh, yeah.
Dual-stream requires this really frequent concatenation and splitting of your conditioning and latent tokens. You have to do it before and after attention within every single transformer block.
Because the modalities have to talk to each other, but they're stored in separate streams.
Right. And when you are splitting those tensors across multiple GPU boundaries, like over NVLink or InfiniBand, that all-to-all communication overhead is just a killer.
Right. You end up bandwidth bound instead of compute bound.
Exactly. Your GPUs are literally just sitting there waiting for data to arrive. So by processing a continuous sequence in a single stream, LingBot-Video radically simplifies all the communication patterns across the cluster.
Which makes sense.
When you are scaling up to handle 1 million plus token spatiotemporal sequences, which you need for long horizon robotics, maximizing that MFU is really the only way the math works.
Okay, that makes total sense. The MFU argument just wins out when you are dealing with sequences that massive.
Yeah.
So we have this highly efficient single stream foundation. Let's talk about how they scale the parameter count to actually learn the physics of the universe without making the inference time impossibly slow.
Well, you have to decouple your total parameter capacity from your active compute.
Right.
And they do this by replacing the traditional dense feed-forward network inside the transformer blocks. They swap it out for a DeepSeek-style sparse mixture of experts layer.
Which is so crucial because if you are dealing with dense layers, every single token has to pass through the exact same set of parameters.
Yes.
And when you are trying to simultaneously model highly asymmetric domains like, I don't know, the rough spatial texture of a brick wall versus the chaotic temporal motion of splashing water,
Right.
forcing all those tokens through one dense pathway creates severe subtask interference. The gradients literally fight each other.
Exactly. We call those parameter-level gradient conflicts, and sparse MOE solves this. But LingBot-Video doesn't just use any standard MOE setup. They use what's called fine-grained specialization.
Okay, fine-grained.
Yeah. So instead of dividing the parameters into a few large experts, say routing a token to 4 out of 64 experts, they divide the parameters into many smaller experts. For example, routing to 8 out of 128 experts.
Let's break down the math on why that matters, actually, because intuitively, 4 out of 64 sounds easier to manage, right?
It does sound easier. And, a coarse 4 out of 64 routing setup might even use a similar amount of active parameters and FLOPs per token, but the fine-grained 8 out of 128 setup consistently outperforms it.
Why is that?
Because of the combinatorial routing space. The number of possible unique pathways a token can take when choosing 8 from 128 is astronomically larger than choosing 4 from 64.
Oh, wow. So it gives the model a vastly larger vocabulary of execution pathways to handle different visual modalities and noise levels.
Exactly. And they structure these experts brilliantly, too. They utilize what they call shared experts and routed experts.
I really like to think of this architecture like a university.
Yep.
Yeah, like the shared experts are the core physics curriculum that every single student or token has to take. Gravity, basic spatial consistency, object permanence, those experts are always active.
Right.
But the routed experts are your hyper-specialized guest lecturers. You only route a token to them when you actually need them. One lecturer specializes in fluid dynamics, another in rigid body collisions, another in high-frequency lighting changes.
That university analogy is spot on.
Mm-mm.
The shared experts isolate the common priors, which means the specialized routed experts don't have to waste parameter capacity redundantly learning basic spatial consistency over and over again.
Which is so efficient.
It really is. But if you've ever trained a MOE model, you know the classic pitfall waiting for you here: routing collapse.
Right. What happens if every single token decides that the fluid dynamics expert is the only one worth talking to?
Exactly.
The load becomes entirely unbalanced, one expert gets overloaded and bottlenecks the whole system, and the other 127 experts just sit idle.
And traditionally, the field fixes this by just slapping an auxiliary loss function onto the model. You mathematically penalize the model during training if it doesn't distribute tokens evenly.
But there is a massive flaw with that, isn't there?
A huge flaw. That auxiliary loss acts as a competing gradient. So the model is suddenly forced to choose between minimizing the actual diffusion denoising loss, making a good video, and satisfying the router penalty.
Which inevitably degrades the overall generation quality.
Yeah. So LingBot-Video just drops the auxiliary loss entirely.
Really?
Yeah. They use an auxiliary loss-free load balancing strategy based on dynamic online bias correction.
Okay, dynamic online bias correction. How does that actually work under the hood?
It's a very elegant mathematical trick. They introduce a dynamic correction bias term for each expert. During training, this bias is updated online at every single optimizer step, based purely on the sign of the expert's load deviation.
Okay, so tracking if it's over or underutilized.
Exactly. If an expert is receiving less than the average token load, its bias is incrementally increased. This makes it artificially more attractive to the router for the next batch.
And if it's overloaded, its bias drops.
You got it.
Wait, though. If you are artificially changing the routing scores with the bias, doesn't that just mess up the gradient flowing back through the affinity scores?
And that is the genius part. The bias is only used for the top K argmax selection, meaning it only decides which experts the token goes to.
Oh, I see.
But once the experts are chosen, the actual rotting weights applied to the token's representation are calculated using the pure, unbiased affinity scores.
That is so smart.
Yeah, so the gradients flowing backward through the network remain completely uncorrupted by the load balancing mechanism.
That is incredibly clever. So what is the ultimate payoff for all this architectural engineering? Give us the scaling numbers.
Okay, the numbers define what we call cross-compute dominance. They built a 30 billion parameter MoE model. But because of this sparse routing, it only utilizes 3 billion active parameters per token. And when evaluated at a 1 million token sequence length, this MoE 30B model achieves 3.18 times faster inference compared to a standard dense 30B model.
Over 3 times faster for the exact same parameter scale. That's huge.
It is. But the kicker is the loss curve. In terms of training loss and representation power, that MoE 30B model closely matches the performance of a dense 14 billion parameter model. But it only requires the active compute budget of a 3 billion parameter model.
That is a staggering efficiency gain.
Truly.
But we have to pivot here for a second because, a massive, say, 120 billion parameter MoE model with perfect architecture is completely useless if it's only trained on cinematic drone footage from YouTube.
Oh, totally useless.
If you do that, it's just going to generate really beautiful, completely physically inaccurate videos. So how does LingBot-Video actually learn embodiment?
You hit the nail on the head. Internet-scale video provides incredible visual diversity, but zero guarantee of physical fidelity. So to solve this, the researchers built a massive data profiling engine. And it tags every single piece of training data across 5 dimensions: structural, semantic, motion, camera, and quality.
And they use this engine to augment standard internet video with explicit robot-oriented footage. We are talking manipulation tasks, indoor navigation, egocentric perspectives from robot arms, that sort of thing.
Yes, and the most critical part of this profiling is actually how they handle motion.
How so?
Well, if you want an AI to learn how a physical object moves through space, you cannot have it confusing the object's independent motion with the camera simply panning across the room.
Oh, right. Like if a car is parked but the cameraman is squinting past it, the pixels of the car are moving rapidly across the frame, but the actual physics of the car are static.
Exactly. So they utilize a geometry-grounded point tracking system called LocoTrack. It explicitly decouples camera motion from actual subject motion.
That makes a lot of sense.
Yeah, it calculates the global homography, which is essentially estimating how the camera itself is moving or rotating. And then it subtracts that global pixel shift.
Leaving just the true motion.
Right. What's left is the independent motion vectors of the objects in the scene. This allows them to filter out near-static videos that might artificially get a high motion score just because, the camera is shaky.
Okay, so all of this meticulously profiled data then feeds into what they call a world knowledge topological graph.
Yes.
Which is this hierarchical semantic tree of visual concepts and physical actions. But from an ML practitioner's perspective, I have to ask, if you are scraping massive amounts of internet data mixed with robot data, how do you avoid the model just memorizing generic, easy data? Like there are millions of hours of dash cam videos of cars just driving forward on a highway. How do you force the model to learn complex physics instead of just saturating on that easy motion?
That is the exact problem the world knowledge graph is designed to solve through dynamic balancing.
Okay.
It isn't just a static database. It actually acts as a control surface for an automated data curriculum. After the initial pre-training stages, they aggregate the model's denoising loss and map it back to the specific semantic and action nodes on the graph.
Ah, so they can see exactly which physical concepts the model is struggling to understand.
Yes. A high denoising loss indicates a hard or rare node. Things like complex hand manipulation, intricate physical contact, or, long-tail human activities.
The tricky stuff.
Exactly. So the system automatically upweights those specific nodes in the sampling mixture for the next training stage.
And vice versa for the easy stuff.
Right. For nodes with very low denoising loss, like your dash cam example of a car driving straight, the system identifies those as saturated easy modes and actively downweights them.
So it's an automated self-correcting curriculum. It literally forces the model to constantly eat its vegetables, so to speak, rather than just filling up on easy, repetitive data.
And that data curriculum is absolutely vital for moving from passive generation to active world modeling. But pre-training on curated data only gives the model a raw understanding of physics.
Right. It doesn't mean it will actually listen to you.
Exactly. How do we actually constrain this model so that it obeys specific robotic commands without hallucinating?
Well, we have to align it. And this brings us to the post-training alignment phase, where they introduce a multidimensional reinforcement learning reward system.
Right.
They aren't just rewarding the model for making a video that looks aesthetically pleasing. They are evaluating task completion and physical rationality.
Yeah.
Did the robot arm actually reach the target? Did the block fall correctly when dropped?
But implementing a physics-based reward system in a diffusion model is mathematically treacherous, especially when you're using flow matching and stochastic sampling.
Why is that?
Well, standard practice in the industry right now is to use an SDE stochastic differential equation conversion to inject noise and explore the policy space during RL.
But the paper explicitly states they avoid standard SDE conversion. They introduce something called coefficients preserving sampling, or CPS. So why throw out the standard SDE?
Because of the Euler-Maruyama step used in converted SDEs. That step injects variance proportional to the step size to explore the space. But if it isn't scaled perfectly, it injects way more noise than the actual inference schedule prescribes.
Oh, I see.
Specifically, at high noise levels, the diffusion coefficient literally explodes. You actually have to apply an extra clipping patch in the code just to keep the training stable.
Yikes.
Yeah, and all this excessive noise leaves visible, high-frequency artifacts in the latent state.
So using standard SDE is basically like trying to grade a student's complex calculus test while someone is actively erasing the numbers on the page.
That's a great analogy.
Like the reward model is trying to evaluate the fine-grained physics of the generated video, say, contact points between a hand and an object. But the SDE has injected so much artifact noise that the reward model gets corrupted, useless scores.
That is a brilliant way to conceptualize it. CPS stops the erasing. It is mathematically constructed so that the total noise after the transition matches the training schedule coefficient exactly.
Okay.
By doing this, the sample stays strictly on the marginal path of the deterministic sampler.
Yeah.
This guarantees that your reward model is always evaluating clean, artifact-free videos. And when your latents are clean, your physics-based reward signals become vastly more accurate.
That's fascinating. They also pair this with something called negative-aware optimization during the alignment phase, right?
And they do.
My understanding is they are keeping an exponential moving average, or EMA, copy of the active policy, but how does that actually prevent the model from gaming the reward system?
Because when you are fine-tuning a policy with RL, models are notoriously lazy. It's very easy for the model to experience mode collapse, where it finds one specific weird way to trick the reward model into giving a high score, and then it just keeps generating that exact same scenario over and over.
Right.
By maintaining an EMA of the policy, they create a trust region bound. The EMA basically acts as an anchor. It regularizes the active policy, preventing its weights from drifting too far or changing too rapidly away from the pre-trained physical priors during fine-tuning.
It's like a rubber band that snaps the model back if it tries to wander off into hallucination territory just to chase a high reward score.
Yeah.
So we have this highly efficient single-stream MOE architecture, an automated physics data curriculum, and an artifact-free RL alignment phase. Let's get to the bottom line for the engineers listening right now. Does it actually work as a physical world model?
The benchmarks are highly compelling. They evaluated LingBot-Video on our bench, which specifically tests robot-centric spatial interaction scenarios.
Like, can the model accurately predict the outcome of a robotic arm moving an object?
Exactly. And LingBot-Video scores 0.620 on that, beating out notable models like CDance 1.5 Pro and WAN 2.6.
Wow. And what about broader physics outside of just robotics?
That is where Physics IQ Verified comes in. It explicitly tests predictive consistency on real physical processes.
Yeah.
Gravity, fluid dynamics, rigid collisions. LingBot-Video scores 40.4, taking first place among all open source models and beating out Cosmos 3 and Honeywell Video 1.5.
So, to synthesize all of this for you listening, LingBot-Video proves that a single-stream, fine-grained, sparse MOE architecture isn't just a theoretical toy for video. It is a highly efficient, mathematically viable path for scaling models to handle the massive million-token sequences that embodied AI demands.
It really is.
By decoupling capacity from compute, automating a rigorous data curriculum, and fixing the noise issues in physical reward alignment, they've built a real foundational step toward a true implicit physical simulator.
It is a total paradigm shift for how we think about video models. And if you follow this trajectory, it raises an incredibly provocative question for the future.
Oh, what's that?
Well, right now, LingBot-Video routes its internal expert networks based on visual tokens and text instructions. But if this model is truly bridging the gap between digital creativity and physical actuation, what happens when we start wrapping those sparse experts based on direct proprioceptive feedback from physical robots?
Oh, wow. You mean like feeding live joint angles, motor velocities, and torque sensors directly into the Mo router alongside the video?
Exactly. Could these sparse video foundation models soon become the literal brains that we download directly into a robotic chassis? Brains that have already mastered the complex physics of the world in latent space just by watching it, and simply need to map those latent predictions to physical servos in real time.
That is a staggering thought to leave off on. We've gone from predicting pixels to predicting physics, and soon predicting physical actuation. If you want to explore the architecture yourself or dig into the code, the LingBot-Video checkpoints are fully open source and available right now on Hugging Face and GitHub. Thank you for joining us on this deep dive today on AI Paper Slop. We will see you next time.